Another thing that we can look at when discussing the Bohr model is that when electrons absorb energy, they jump to levels farther from the nucleus which are higher in energy. This is referred to as an excited state. So this introduces two terms, a ground state and an excited state. So if we look at our nucleus down here, and we can look at these different levels from the nucleus, and these are integer whole numbers. So if an electron starts in the n equals 1 level and gets excited to either up to the n equals to 2 or the n equals to 3, it's going to absorb energy. So it's going to take energy to go from the ground state to one of these excited states. So typically when this happens, we are going to absorb a photon. If, on the other hand, we have an electron that starts at n equals 3 and it goes down either to n equals 2 or n equals 1, we can say this emits energy. And typically this emission is in the form of light. So what we can do here, and using this information here from Bohr's model, we can calculate the energy difference when an electron changes orbitals. And they're going to relate to that spectrum that we saw in the previous slide. So our change in energy, or our delta E, is going to be the final state minus the initial state, which is going to equal negative RH divided by NF, that quantity squared, minus RH, or minus negative RH, divided by Ni, that quantity squared. And when Bohr manipulated around these equations, he came up with an equation that said delta E is going to equal to negative 2.18 times 10 to the minus 18th joules times 1 over NF squared minus 1 over Ni squared. And this equation right here is going to be our Bohr equation that is going to show us or tell us what the energy is that's either emitted or absorbed in exciting an electron from a ground state to an excited state, or emitting an electron from an excited state down to a ground state. This negative sign here is going to indicate whether that electron is either absorbed or if it's emitted. So if Ni is greater than Nf, our delta E is going to be negative, and therefore energy is given off. If Nf is greater than Ni, our delta E is going to be positive, and the energy is going to be absorbed. So if our Nf is going to equal infinity, we completely remove an electron, or we completely remove an electron away from the nucleus. This is called ionization. And this is going to be a big property that we are going to discuss in the upcoming chapters. So essentially, in this case, if we look at ionization, that's completely removing that electron. So if we looked at an atom of hydrogen in the gaseous state, and we wanted to make it H plus an electron, this is what we refer to as ionization. And if we want to look at the energy that it takes to remove that electron, we call that ionization energy, and we abbreviate that with a capital I and a capital E. So for hydrogen, the ionization energy, starting with the ground state, is delta E equal to our H, our Rydberg constant, over 1 squared, which equals 2.18 times 10 to the minus 18th joules. And this is the constant that comes outside of the Bohr expression. So Bohr's model worked amazingly well for the experimental results for hydrogen, but when more than one electron is involved, the theory falls apart. So this works amazing for hydrogen. We can explain everything in the hydrogen line spectrum, but when we try to apply this to something like helium, it completely falls apart. It doesn't work. And when we look at these different spectra, we have one electron systems, which Bohr's formula works great for, and then we have many electron systems where it doesn't really work well. And this is our first indication that electron-electron interactions are going to be very, very, very important when we try to look at the model that we have for an atom. So we're going to have to discuss some more theories and go into a little bit more detail in a couple of other sections, and we'll start that in the next video with the wave behavior of matter.